Okay, I think we've about ready to get started here. So for those of you just joining our session, welcome to your first step to space in parabolic flight. I just want to quickly introduce our speakers today. Oh, before I do that, sorry, let me just state that attendees are welcome to post questions in the Q&A box, and we'll do our best to address them at the end of the talk. But we have three presenters today, and I just wanted to quickly introduce them. First off, we'll have Michelle Peters, Directors of Research and Education at Zero G. And then we'll move on into Mars Coutinho, is that right?
Cutno.
Cutno, pardon me, CEO of PhysioWave. And then Stephen Collicott,
Yes.
correct? Professor of Aerospace Engineering at Purdue University. So I'm going to let them explain more about what they do and who they are. And I believe, Michelle, the floor is yours.
Well, thank you, and welcome everyone. My name is Michelle Peters. I am the Director of Research and Education for Zero Gravity Corporation, more commonly known as Zero G. I've been with the company for going on 17 years now, and in that time have myself completed over 200 flights and several thousand parabolas. I have written the research program, which has been in operation at Zero G for over 12 years. And has been highly successful. So with that, let me go ahead and get started. I just want to share with you a little bit about our company, what we do, and then talk about some of our research programs. So Zero Gravity Corporation is the name of the entity. And what do? We go weightless. We are a parabolic flight provider. We operate a specially modified Boeing 727 aircraft. It flies in parabolic arcs, and in those parabolic arcs creates a weightless environment, which allows the participants on the aircraft to float, flip, and soar as if you were actually in space. Oftentimes people think that this is some kind of a simulation or that you can do it on the ground. You cannot. It is not a simulation. It is real life minus gravity. So a little bit about our company history. Zero Gravity Corporation is on a mission, and that mission is to advance lives in space and on Earth through zero gravity experiences and conduct research that make dreams a reality. Our company was founded in 1993 in the US and have offered public flights since 2004. Doctors Peter Diamandis, a name you may be familiar with, astronaut Byron Lichtenberg, another gentleman you may be familiar with, and Ray Cronise, who was an engineer at NASA, worked very closely with the FAA for 11 years to create, test, and certify Zero G's weightless experience. We also obtained NASA's contract as their sole parabolic flight provider to conduct research from 2008 until 2015. During that time, we operated from the Johnson Space Center in Houston, Texas, to fly many, many different types of research under that government contract. In about 2020, we brought in a new management team. Matt Goad, our CEO, and Allison Odyssey, our COO, have really transformed our organization, our company, by doubling the staff, obtaining significant investment, fostering key relationships around the world, and really implementing continuous process improvements so that we are now recognized globally and respected as one of the world's only commercial flight providers for parabolic flight. We've been in operation for 18 years or more. To date, we have provided 800 or more flights, hosting more than 17,500 clients from around the world. We have a robust research platform with more than 12 years successful missions, and we test complex hardware, develop extensive partnerships across a spectrum of industries. So let me tell you a little bit about how parabolic flight works. Working with the FAA and ATC, oops, excuse me, let me go back a slide here. So working closely with the FAA and air traffic control, we obtain a designated airspace. And in that airspace, our specially trained pilots are going to perform aerobatic maneuvers, which are referred to as parabolas. Takeoff and landing are about the same as any commercial flight. And once we get up to 10,000 feet, with the captain's approval, passengers can move into the floating zone. Before we start a parabola, G-Force One, our aircraft, flies level to the horizon at an altitude of approximately 24,000 feet. The pilots then pull up and gradually increase the angle of the aircraft to about 45 degrees to the horizon until we reach an altitude of about 32,000 feet. During the pull-up, passengers feel about 1.8 Gs on their body. We have them lay flat on the aircraft floor. And then the plane is pushed over the top, as you can see here. For about 20 to 30 seconds, everything and everyone in the aircraft is weightless. Immediately after that, there is a gentle pullout, which allows passengers to stabilize on the aircraft floor. And then the maneuver is repeated anywhere from 15 to 60 times, creating a variety of weightless operations throughout the flight. We also fly parabolas designed to achieve lunar gravity, which is 1/6 of a G, Martian gravity, 1/3 of a G, and we can also offer asteroid gravities. We do these by flying larger arcs over the top of the parabolas. So what does 0G do? 0G is for everyone who comes and flies with us. We offer corporate events, we offer promotional flights, research and training. We do education programs to inspire teachers and students, and we also do TV and film production. Today, we want to talk a little bit more about research and training. So the goal of this presentation is to introduce you to the first step to space. The goal here is to achieve the highest possible readiness for equipment before launch so that when it goes, it will achieve mission success. Several of the advantages for parabolic flight: you get to fly with your payload, you have real-time monitoring of your experiment, so you're right there with it. You can troubleshoot the experiment if something starts to go wrong. Perhaps you can stop it midstream. You also have the opportunity to firsthand observe any breakthroughs that you may not be able to observe if you were not flying with your payload. You can do multiple flights in 1 week to replicate or perfect different results. And then you also have, while the aircraft is on the ground between flights, you still have time to work on your payload to make additional smaller and pre-approved adjustments before your next flight the next day. And finally, it is far more cost-effective to experience failure on a parabolic flight and then come back from that and improve than it is to go to space, have a failure, and then come back to Earth and have to replicate the experiment to try to improve for success. You know, we send astronauts, I have a statement down here at the bottom, we train astronauts extensively and many times to include parabolic flight prior to their mission. Their hardware should have at least the same level of preparation and be ready to go. So here's a little bit, a short list of some of our researchers that have flown with us. Today, you'll hear from a couple of those researchers, but a few others. We've flown with Chosun University out of South Korea. We've worked with the Japanese Aerospace Agency, the University of Florida, Space Florida, MIT, Vostok out of Australia, and a number of domestic and international clients. Many people ask us what types of research we fly. Here are just a few examples. Fluids experiments, monitoring brainwave activity during different types of parabolas and flights, body mass measurement, propellant tank design, ion engines. We do a number of medical experiments on board. We have also had the universities work on surgery in space, different types of motion control and analysis. waste removal systems, what types of space materials can fly and what are best for flights, different types of array deployments. And I wanted to share a few comments that we've had from researchers over the years. Essentially, most of our researchers reply that being able to experience microgravity and better understand the environment, as well as have hands-on access to their experiment while they're flying, is really key to success. We've even had the former Associate Administrator for Commercial Space Transportation at the FAA comment on the exceptional nature of our product and of our staff. The training that Zero-G offers provides an outstanding opportunity for crew members to experience firsthand the reduced gravity environment so uniquely associated with spaceflight, and allowing crew members to have that experience prior to launch definitely will help them be better prepared for their missions. So it was a real high honor to have the FAA former Associate Administrator make that comment. And then here at the bottom, a United Space Alliance payload engineer who worked on several experiments indicated that even though he had years of design work and years of experience and education, until he came and flew with us and he really understood what the environment was like, designing for space took on a whole new meaning and a whole new perspective for him to better do his job. For more information on Zero-G and perhaps to book a seat, this is my contact information, michelle@gozerog.com. There's my number. It's all over the website, gozerog.com, down at the bottom. And thank you so much. And at this point, I will turn it over to the next presenter. Thank you.
Okay, how's everyone doing? So I'm Marsh Cutno. I'm going to talk a little bit about medical research in microgravity and how you can use parabolic flight as a pathfinder for suborbital and orbital experiments. A little bit about my background. I'm board certified in emergency medicine, and in the mid to late 90s, I worked as a space shuttle medical support physician at the Kennedy Space Center. Ended up doing aerospace medicine residency elective at the Johnson Space Center in 1998. And I have several thousands of parabolas as well, doing research in microgravity, which, as Michelle was saying, you develop a intuition about microgravity that you don't get on normal ground experience. So when you're designing for the type of research that's going to be needed for suborbital and orbital space flight, it's very helpful to have this experience, and you can get it no other place on Earth. I'm also a senior aviation medical examiner for the FAA, and currently I am the CEO of PhysioWave, which I'm going to talk about a little bit later in this presentation. So what we're going to talk about, the orbital medicine thoracic drainage device, which is a medical drainage system for the microgravity environment, and thoracic PARG, which is the patient aspiration and reduced gravity, and a project out of Stanford University, the ballistic cardiograph, which is a non-invasive hemodynamic monitoring in microgravity, which has evolved to commercial development to the company PhysioWave, which I'm now CEO of. So why do you want to do research in parabolic flight? Well, they serve as a place to work out the kinks, figure out what works, which doesn't, and they're pathfinder missions for these suborbital and orbital research. You need similar methods in preparation when you're working for a suborbital flight campaign as you do for a orbital or suborbital flight campaign. And this just is the ideal platform for all types of innovation. On the left, you see that that's me intubating a mannequin. That mannequin was designed for use on the International Space Station for training astronauts on how to perform medical procedures in microgravity. You're able to intubate it, you're able to do procedures to it. And on the bottom right, you see a couple of the astronauts training. Those are both physician astronauts learning how to do things that they know how to do well on Earth, but to do it with the changes that you have in microgravity. So NASA's understand this, and NASA has done this for many, many years. But the beauty of Zero-G Corporation is non-NASA people can do it as well. The plane that they have, very useful and incredibly designed correctly for doing experiments. On the right, that is a shot of one of my experiments loaded on the plane. And you're able to use this plane to do all sorts of cool stuff that you can't do on Earth. The microgravity drainage device, as you see in the top left, originally flew on zero-G a number of years ago, and it evolved. It's had, I think at this point, approximately 12 campaigns with iterative improvements. After significant improvements on parabolic flights, it then went through 2 iterations that flew suborbitally. So you can see down here, this was the first suborbital flight, ended up flying on the first FAA-approved flight of Blue Origin's New Shepard aircraft, and here's a shot of that just after the launch. And then we had a collapsible version, which we created and flew, and that flew on a later flight a few years later. So we were able to take this much large device, and through the experiences that we got on zero-G, able to shrink it down into a much smaller device that you can see here in the bottom right, and make it work efficiently, and it functioned perfectly in the suborbital flight regime after we were able to do that. Now, we took the lessons we learned from this, including everything from fluid management, how to handle hazardous material, because this is a medical device that was actually designed to function with human blood. So we worked with zero-G and were able to get the hazardous material stuff. They were very good to work with us. And then that hazardous material handling also went on into the suborbital flights. And we were able to get all that stuff done. And now we have integrated into a much larger project. We are integrating with a surgical system with Purdue and University of Louisville. And it is an entire surgical suite of which we are providing the suction portion. So here's the suction portion down at the bottom, and up here is the microgravity surgery suite. So this is designed for astronauts in the future to be able to do invasive medical operations on astronauts, and learning it in parabolic flight has enabled us to make leaps and bounds of progress that we would not be able to do if we had to wait until an orbital flight was available. Next, I'm going to talk a little bit about measuring cardiac output and pulse wave velocity in space. This is the ballistic cardiograph experiment. It was a joint experiment between Stanford and University in orbital medicine. It was a device able to measure non-invasively the measurement of blood flow from the heart through the body. So we were trying to figure out how can you measure cardiac output of an astronaut. And we developed a system that measures what's called the ballistic cardiogram, which, if you think about it, is a little bit like a seismograph for your heart. So every time your heart beats, your body shakes and moves a little bit. And so we were able, in microgravity, to develop a system that's able to measure that output and then figure out how strongly the heart is beating. And from that, we're able to measure what's called the pulse wave velocity, which is the measurement of how fast your blood is moving through your aorta. Now, pulse wave velocity is important because when you get hardening of the arteries called atherosclerosis, that leads to heart attacks and strokes. It turns out this technology is able to measure that, and that can give you a measure of your cardiac risk. Now, this was originally developed on parabolic flights and tuned, but it is now on orbital flights and is scheduled to be shortly flown to the International Space Station for experiments with the astronauts. Now, this was a shot of the Stanford experimental group, and so it was a fairly large experimental group. All of them got to fly and experience weightless, so that incredibly contributed to their knowledge in the experimental design and improvements needed to develop space hardware. So here's a shot of the hardware in the plane. You can see that on the left here, the researcher is standing on the device that's scaled, and then we have a couple of other researchers over here. They are floating weightless, and so we are able to measure their heartbeat while they're floating and while they're restrained, and so we're able to compare all this. And this helped with the development of our algorithms and our technology that has led to a significant improvement. So from this original experimental device, the technology has now been spun out as a digital healthcare startup, spun out of Stanford. The device has achieved 510K medical clearance from the FDA, and the company PhysioWave is now preparing for medical and consumer products. So expect to see this research device evolve to a consumer device available in the next few years on your shelf. So with that, I understand we're gonna put some questions to the end, but I will now hand it over to Professor Stephen Collicott from Purdue.
Thank you. Thank you. Let me pull up a few slides here. It's great to be here. Thanks to Michelle for including me. So yes, I'm a professor at Purdue University, School of Aeronautics and Astronautics, which is part of our engineering college here. And I'm in my 32nd year. We'll talk a little bit about background, and let me talk also about education uses of parabolic flight. And then
Terribly sorry, Stephen. We're having trouble seeing your entire slide. I don't know if you could zoom out, possibly. Yeah, it's at least maybe I'm the only one having that issue, but I can only see, yeah, that I can see the full slide, and I don't know, yeah, that one, it's cut off on the left, at least for me.
okay,
Yeah, I don't know if there's some way to.
it doesn't work with full screen.
Yeah, it doesn't
Okay.
really.
Maybe I have a fatter screen. Okay.
Yeah, it could be.
I am able to see. I am able to see the whole slide. Marsh,
Oh,
are you
okay.
able to see?
I am able to see the whole slide
Okay,
as well.
so it's just me. Sorry.
Okay.
Thank you.
So, and yeah, we'll talk also about research, and so, yeah, I got involved with zero gravity topics in 1981, long ago, as a summer intern engineering student, but then set it aside for a decade or so. And in '93, I began back into it with the Gravity Probe B satellite program, managing liquid helium in a spinning vehicle in orbit. And these days, since then, I've been doing both scientific research in fluid physics and industrial strength zero gravity fluids for propellant control in spacecraft. It's been a lot of fun. I've been enjoying zero G flight experiments since '96. I've had 49. Fortunately, in the early days, I started to keep a log, so I know I've had 49 parabolic flight experiments, and we're building 3 more. Right now, I've done work in drop towers and space station, and 8 Blue Origin suborbital experiments and up aerospace and Armadillo and Exos. And we're building my first 2 Virgin Galactic payloads right now, and we've done 5 Neutral Buoyancy Lab spacewalk tool tests. So what this means is I've found a really fun way to do the professor's job. And it's great. All right, so most of these experiments are built with our students. I've integrated my funded research program with my teaching, undergraduate teaching, in this class called Zero Gravity Flight Experiment. We've got over 1,300 students in this since '96. Nearly 300 have flown in parabolic flights, and some very, very successful graduates coming out of our department that I did my part to help them along. There's some pictures, type of things we do. Upper left is about 4 a.m. or 5 a.m. at Spaceport America with Armadillo. Here with the big white zero G airplane in front of us, and a cold to the right of that, a cold morning with Exos out at Spaceport America. Upper right, there's a couple of Purdue students teaching the NASA divers in the Neutral Buoyancy Lab how to manipulate and operate the spacewalk tool they've created in my class. Lower right, a couple of students, Jonathan and Brad, long ago in the NASA plane, working a fluids experiment. Center bottom, 4 young men in red shirts. That's actually a high school in Texas with that's the rocket the high school built, and we had a payload to launch on that. And lower left, one of the Blue Origin New Shepard flights. You see the capsule in the background. I'm in the Purdue shirt, of course, and Stephanie and Hannah with us, and Jeff Bezos right in front. And so a lot of fun things, and even beyond flight test, upper left, I got to do U.S. Senate testimony one time. That's me on the far right at that table of three really distinguished people and me. Upper right there, I had children's television, another surreal experience, just like Senate testimony. The bottom row, I've been working with the Commercial Spaceflight Federation, and for 9 years, I chaired the Suborbital Applications Researchers Group, where we do a lot of things in the industry. Coincidentally, that is Dr. Cutno on the left in front of the F-104. I'm at the inlet And if you saw news of plant growth in lunar regolith, about 2-3 weeks ago, that hit the news a month ago, that big news. This researcher on the far right, Dr. Annalisa Paul, was one of the investigators there. So a great group of people. All right, so what do I get to do? Oh yeah, and 11 days ago, there I was at the Blue Origin launch site in Texas for that launch attempt on Monday the 12th. All right, education uses, parabolic flight. I've done a couple things I thought I'd share. The simplest is this. We've had middle school students just do an add-on experiment when I've had a NASA payload and, oh, there's some room over here, shoebox size, volume. It's easy to make extra room. They had bolted on 2 fluids vessels or springs and magnets or whatever, and a GoPro camera just in its own little box. It's out of the way. It sits there. Other than turning on the camera, there's no operations for it. And it's the simplest way to involve students and good way to get started working with students in your program. And it's very cheap. One, since you have the flight already, I had the flight already from NASA. So, it's not a big budget thing. It's not a big program. Students or classes that are interested in something, you can work with them this way. If you're a teacher in the audience, this means, look in your neighborhood, around your state, which professors are flying things on the plane, and strike up a collaboration with them. A second way I've done this is the K-12 handheld payload. Okay, I'll show you some pictures of what's basically a cheese puff jug. It works as the second containment for a spinning liquids experiment inside. We actually had Nickelodeon slime in there, and a GoPro. And aside from the GoPro, it was under $100. So building it can be very, very easy, very accessible. This November, we're flying a K-12 teacher and a different cheese puff jug experiment, looking at concepts of this for high school science, like an angular momentum, moments of inertia, changing reference frames, gyroscopes, and whatnot. So it looks like an Indiana high school up north here that has an engineering class that one of their teachers there will be flying with us. And I want to point out too, I checked last night, it says today, but I checked last night on Michelle's website. A single seat handheld experiment price is $8,500. And that's half the cost of high school football uniforms. Any school that can afford football can afford 0G, okay? And any of you in the audience from Texas, it's probably more like a third or a quarter of your football uniform prices there. That's my usual joke. A third way, a friend of mine, oh yeah, here's the cheese puff jugs. On the left, that's me and one of my seniors, Dare Adebanojo, just before he graduated. The one in front of him is you can see the green Nickelodeon slime. The jug in front of me was a solid mechanics or different fluids payload our students put together. On the right, you see Mr. Earl Coleman from McCutcheon High School here in Lafayette, Indiana, and he's flying our first iteration of this angular momentum payload. And so these are easy to do, and I think it's a great addition to the 0G's product line that they have this single seat handheld experiment option for this affordable cost. A friend of mine, he's been mentioned before, from University of Louisville, collaborating with Marsh and I on that surgery project. He likes to embed a teacher. That is, bring the teacher into his laboratory a number of times throughout the semester or the year, and then fly the teacher as part of his experiment team. And what does that cost? Well, that takes up one spot that he would normally have for one of his students, but this is another option too. And if you're getting whole hog into K-12 outreach, or if you're a teacher online here, this is a great thing to aim for. Try to find somebody in your region who you could interest in this. For research, look, the parabolic flight is both a destination for science, for research, and it's a step to space. Okay, a lot of us use parabolic flights to answer questions and solve problems in science and engineering because it is so accessible. You don't have to wait the long time to get up to space stations. Space station's biggest thing we've ever had in orbit. It's a great laboratory, but it's not big enough. Okay, it's hard to get up there. And whereas getting on the airplane is simple. So usually I look at the airplane not as a step to space, but also as a destination. I'm going to get my job done in the airplane and not have to wait 6 years to get to space. That's changing. And so when we do use it as a step to space, it's to prepare ideas or hardware for long duration microgravity. Sometimes it's testing out devices and designs, and I'll talk about one here in a little bit. Other times it's to flesh out your ideas to say, well, I'd like to do this in space. How should I do it? And doing it in short-term weightlessness while you, the researcher, you, the expert, is in your topic is looking at it, as opposed to an astronaut who they're wonderful people. They're really smart, really capable, but they're still not you, the expert in your field in general. So being able to be there with it and try things is a great part of parabolic flight. So as a destination example, conformal propellant tanks. As satellites are getting smaller, there's 3 different things coming together. We won't get into what those 3 are, but they're technical and they're marketplace drivers that are causing people to make changes in how satellite propellant systems are designed, and that actually reduces the need for a strong pressure vessel for a tank. And so we can go to exotic shapes of credit or cell phone. Students called this one on the upper left, and you can see an L shaped on the lower left. Lower right, it's a quarter arc. We have a traditional sphere in there just kind of as a control case, and it's a cube and rectangles and whatnot. These we actually had 3D printed, and we put in something called a propellant management device. It's sheet metal vanes. You'll see a picture coming up. And these vanes, these pieces of sheet metal create corners, and the corners in 0G is what the liquid wants to wick into. That's how people for 60 years have controlled liquids in spacecraft. It's one of the ways. But there's still, when we go to new tank shapes like this, where the tank now has corners, there's all kinds of new questions. And so this was funded work here. I'll just show you 2 examples. I think the sphere here is really our control case, but I wanted to show you on the lower left, there you can see the sheet metal vanes that I was talking about. And those in the upper row, you see the blue liquid, that's a poor wetting liquid, and the red in the bottom row is a really good wetting liquid. And then the left column is the 3D printed sphere, and the right column is our more traditional machined and polished sphere, just seeing how the 2 compare. Another example here then was the rectangle in the lower right. You can really see how, well, on the lower left, on the left side, you can see the metal vanes in here with the corners at the outlet of the tank, to try to keep the liquid at the outlet of the tank, which is lower left, and drive the bubble up to the upper right. And you can see in the red liquid, that's really doing a good job of positioning the bubble well away from the outlet of the tank. And these are demonstrating to the aerospace industry both the design issues and the design options in this new generation of small sats. Cell phone tanks, just another example there, which actually is probably the ideal case if you have a large propellant that doesn't wet the surface well, which is typical of some of the new non-toxic propellants. So a little overview. Liquids that I've flown, I've watched fly. I just tried to, off the top of my head, think about everything I've seen. People often ask, can I fly this? Can I fly that? The red you saw was silicon oil, and it's a standard test liquid for capillary fluids problems, and we've flown it in space station. Solutions of various glycols and ethylene glycol, human blood, Marsh mentioned, liquid nitrogen. I flew with a colleague's big liquid nitrogen payload in June, and I'll have my own next year. Water, of course, saline, there was fascinating work on 3D cellular printing of organs that tech shot, now part of Redwire in New Albany, Indiana, flew one time. So very successful. Dry powders are not liquids, but they leak. They leak out of containers in zero G, and sometimes more persistently, it seems, than liquids do. It's fascinating stuff. Refrigerants in thermal cycles and refrigeration cycles and flow boiling. So a lot of things, and that's just my exposure. A lot of things can be done. Here's an example of what one of my experiments looks like. This aluminum frame in front of us here. The two young men in blue are two of my, well, one's a graduate student, one's an undergraduate student in aerospace engineering here at Purdue. This was our conformal tanks payload, and there were actually 11 what we call pods. We were just always jamming more and more examples into it. You can see some red and green demo spheres right here in the middle. And we've flown this one several times. You might ask, well, why is there nobody else on the airplane? The seats are empty. And the answer is everybody else is forward. We are the aftmost experiment in this picture. So everybody else is forward of us working on their experiments. It was we don't get a private flight. It was a full flight, but those seats in back are where you sit for takeoff and landing. Parabolic flight as a step to space. My colleague, Isam Mudawar, a professor of mechanical engineering here at Purdue, he's principal investigator on the big flow boiling and condensation experiment in Space Station. It's now up there, it's now operating, it's getting really unique data, powerful data for thermal control system design for future spacecraft. But he spent a lot of time maturing that design in a series of parabolic flights, and liquid and gas management issues were tackled. The liquids don't behave in zero G like you expect them to behave in 1G, and we don't grow up with that intuition of how they're going to behave in zero G. So we always get surprises, and as Michelle pointed out, you're much better getting your surprises in the airplane than once you're up in orbit. You can do instrumentation maturation and proof, and is this thermocouple attached in a good way to survive, and does it work well in zero G, and so on down the list. And they also got preliminary data on some heat transfer work that really helped them size their instrumentation for the choices for the in-space payload, and other contingencies like bubbles in the wrong place, or a dry out of the heater section, or there was one where there was a tube they thought would be full of liquid flowing up, but when they hit zero G, then like all the liquid went to one side and the gas shot through the other side. So you're able to figure these things out quickly and relatively cheaply, as opposed to up in space. So Michelle kind of titled this A Step to Space. I want to show you my June 2011 student team here. 4 undergraduates, that's me, the old guy on the left, obviously, in front of our Purdue banner. We're wearing green suits. This was down at the NASA Reduced Gravity office that existed then, but you can tell from the foam on the wall that this is Michelle's airplane. They were delivering flights to NASA back then. So the young lady next to me, this was she was team leader of this experiment, and this dealt with another way to control liquids in tanks is basically a water balloon inside the tank. And we were looking at the dynamics of that and how the liquid sloshes around. A very successful experiment. So just 10 years later, Sirisha Bandlaw was Virgin Galactic vice president and performed a human-tended biology experiment on a Virgin Galactic flight. That's a great photo of her peering out the window at the Earth. So indeed, parabolic flight on zero G airplane was literally a step to space for this young professional, and we're all very, very proud of Sirisha here at Purdue. There's actually a banner on the side of the building trying to inspire current students with her picture on it and her story. So it's, and the building is Neil Armstrong Hall of Engineering. Neil is also one of our alums, and so I have a cool job I come to every day in Neil Armstrong Hall. But what about the rest of the team? Well, look, December last year, I got picked. I'm going to fly with a Steve-intended experiment on Virgin Galactic, and this was Purdue's press release announcing that. So actually, half of that flight team I showed you will have flown in space will have used zero G's airplane as our step to space. So I know Michelle intended us to talk about experiments, but it's people too. It's a step for experiments. It's a step for people. And that concludes what I had to say today. Michelle?
Thank you so much, Stephen and Marsh. I see we have a couple of questions in the Q&A box. Sean, did you want to address those? Do we have any other questions from the group?
Nothing. Yeah. So it looked like Marsh, you went ahead and typed up one, and then you said you're gonna answer one live. So why don't you go ahead for the live one, if you would, please.
Okay, so the answer is there are a lot of areas in medicine that we are still working on to find a good way to do in the orbital environment. Many of the testing procedures and just the changes of the human body are still being studied extensively. For example, you may have heard a lot about the changes of people's vision in space. Turns out that there may be a gene that makes some people likely to get nearsighted if they're in space for a prolonged period of time. There are also a lot of changes to your heart that we are still understanding caused by the fluid shift, because when you're in gravity, the fluid is pulled down to your legs, and your heart is designed to preferentially push the blood up towards your head. When you are weightless, it turns out that the heart pushes a little extra hard towards the brain. Your face gets swollen, you get chicken legs, and that causes a lot of changes, for example, in your balance, blood pressure, and when you come down to Earth, you get a lot of switches, and then you get diuresis, which means that you get rid of a lot of extra fluid. And just to clarify my typed answer, the question was, how do we do the surgery in the short periods? And what we do is we plan very carefully and chunk the surgery, because we know it's going to be a 30-second segment that we have to work. And so we basically step it a little bit like a time frame or a stop action movie. So we do the 30 seconds of work, hold still, do the 30 seconds of work, hold still. And I see there's a new question called, do astronauts experience symptoms of sickness during parabolic flight training? And if so, are the symptoms the same as those experienced during an outer space flight experience, and what symptoms are most common? And the answer is, I have not seen an astronaut get sick during parabolic flight, but the symptoms for space motion sickness, which is what affects the astronauts on orbit, the most common symptom is nausea and vomiting, and that happens when an astronaut is adapting to zero gravity, and they have some issues with long-term with their vision, and when, like, for example, if you're looking down a hallway of the International Space Station, on Earth, we're used to having the floor down and the ceiling top, but if you are floating for a prolonged period of time, you can get a little bit disoriented if the ceiling is now all of a sudden your floor, and that will occasionally cause some of the space motion sickness during space flight. And vomiting in space is the most common symptom of that. Generally lasts a day or two and then goes away in space.
I'd like to also add, oh, sorry, Stephen, but I wanted to add too, you may have heard the moniker vomit comet. That is specifically applied to NASA's former aircraft, wherein they would intentionally cause motion sickness in passengers to study that very phenomenon. Zero G's aircraft, while we do many parabolas for adventure, fun flying, 15 parabolas typically, we have a very, very low motion sickness rate. We also do research, 30 parabolas, and sometimes more for charter clients who need more space time. And we recommend, if you're concerned, to speak with your doctor. There are some medicines that are available over the counter, and then also some that can be prescribed that will help alleviate any of those symptoms. Stephen?
Oh, I was just going to add that I know from, we have about 27 Purdue alums who are astronauts of various types, that there's a wide variety of responses, from a couple who would show up in the morning at the NASA hangar and say, I want to fly with the Purdue team, to a couple who had great flights in space shuttle, but who tell me I am never getting on that airplane again. So, and a good friend of ours, Marsh and I, works on the neurovestibular system research at Johns Hopkins, and he keeps telling us there is no predictor, and it's a lot of open questions about who's going to be bothered or not. But I've even one of my students who had a hard day is now doing very, very well as an Air Force fighter pilot. So, it seems random.
I would say too, you acclimate, you get used to it over time, the more flights that you do.
Do you equate that to some sort of like similar to motion sickness? Like I have family who can't really fly because they don't fly at all, commercial flights, or they can't go on boats because they get motion sickness. Is this similar to that?
Yes.
Yeah. Okay. Because I believe Michelle, you mentioned the vomit comment, but that's getting it more like high G situations where you take a sharp turn, isn't it? And then the people get sick because of the high G, or am I mistaken?
So I'm going to provide a short initial response, and then I'm going to turn it back over to Marsh for a more detailed medical.
Okay.
So on our flights, what we strongly encourage our passengers to do, especially our new passengers, be it research or for fun or whatever they're coming to fly to experience, as we're doing, you remember the video that I showed, as we're in the high G portion, we strongly encourage everyone to lay down flat on the floor, pick a spot on the ceiling, and just keep your eyes on that spot and not move your head. A lot of times it's the movement of the fluids in your head that can cause those issues. And then as you're standing or kneeling, of course, because the G's are pulling down towards the floor, it's pulling all of that fluid away from your brain and the rest of your body. So that can disorient and make you very uncomfortable. So we encourage, in order to minimize that fluid shift, that folks lay down on the floor during the high Gs, and then they can get up and move around after some of the Gs come off and we start to flow a little bit more. Marsh, did you want to add to that?
Sure. So first of all, people who love sailing and roller coasters always do very well in my experience. What does cause some people to get the motion sickness is the high G portion and turning your head. So if you are able to keep your head still during the high G portion, you've got in your inner ear, you've got semicircular canals, they've got little tiny otoliths in there. Turning your head in the high G makes them spin a tiny bit, and then that can make you feel a little bit nauseated. So as long as you are keep your head still and do not do rapid movements in the high G, everyone does fine.
Which means if you follow Zero G's advice and training that you receive before the flight, you'll probably do okay. And that includes not trying to use your cell phone. A lot of people get sick looking at the cell phone viewfinder as they're spinning, the subject is spinning, it's spinning on the phone. Just Zero G has great videographers and photographers. Let them get the pictures and you'll be much better off.
Let me share too, kind of paying off of that. Some of our flights for research, adventure, there are a number of things that are included when you come and fly, some pretty standard inclusions. You get your own flight suit, which you keep. There's other merchandise that we provide for our fun flights and for research. There are professional photographers on board as well as a videographer. If you're doing research and you have a small specific payload, we encourage you to bring a GoPro or more, depending on what your needs are. For our adventure flights, we recommend that you leave the photography and videography to us. We have mounted video cameras, and then also we provide a videographer. Catering is included for our research flights on the day, and there's a lot of groundwork that goes into your flight prior to arriving. There are payload documentation, FAA approvals. Believe it or not, we are considered the same as any other commercial aircraft. Delta, United, American, Southwest, any of those. Zero G is required to meet all of those safety requirements and then some. in terms of pilot training, in terms of maintenance programs, in terms of any kind of flying that we do. We are an FAA approved and certificated airline.
Wonderful, wonderful.
So just like the other airlines, and you do get the silly instructions on how to buckle your seatbelt. But
I was going to ask that.
Zero G has never sent my luggage to the wrong city, so you're
better. Oh, wonderful! Yeah,
better than usual airlines in that.
Yeah, so wonderful, wonderful. Now, I guess my next question might be more for Stephen. So, Stephen, you mentioned something about containers for propellant, and please forgive me if I missed any step of this, but you said often what they do is have the propellant collects in the corner, and maybe having a gauge of some kind in the corner. Is that what you were getting at?
Oh, I was getting at that by creating these veins that create a corner.
Yeah.
We're able to position the liquid where we want it in weightlessness. So gravity doesn't pull it to the bottom like where the drain is.
Yeah.
But we can use wicking.
Okay. But then,
and actually, this happens on tanks as long as 3 meters I've worked on. So really? Wicking is only relevant here on Earth in very tiny length scales. But up in space, without, in weightlessness, it can be the dominant effect. So the corners create how we position it. And the difference with the new tanks now is that instead of being, circular pressure vessels, they can be all kinds of shapes. And believe me, people are getting awful creative.
I can imagine, yeah.
And the tanks have their own corners for fitting around other things in the satellite.
Just out of curiosity, with the tank having this corner, would it create any sort of turbulent flow for the propellant, or is that much of an issue?
Usually, you're not flowing that fast.
Okay, yeah.
During boost, you're flowing lots of propellant to get off the Earth, and everything's turbulent. But upstairs, it's pretty slow.
I suppose, yeah. Once you're in microgravity, yeah. Okay. Trying to think, I had several questions. That was the other one. So again, this is probably for all of you. I may have some advice on this, but to me, when I think of flying, I think of ears popping. And I don't know, is the plane you use better pressurized or than the average commercial airplane where you don't have the reasonable pressure difference which causes ear popping and such? Are there any distinctions?
The takeoff and landing is pretty much the same as any commercial flight. If your ears typically pop for takeoff and landing, they will also on our aircraft. Pressurization does not change during the parabolas. It remains very stable. So there should be no ear popping during the parabolas. If you're experiencing some type of discomfort, then you would notify one of our flight attendants on board immediately, and we would administer appropriate medical attention at that point.
Wow, sounds like you have everything on board. No, I was just curious because I just got back from a flight where I had a bit of congestion, and the first thing I noticed was, okay, I got to pop the ears because it's always a problem in a commercial airliner. But
yeah, that's from sea level up to 8,000 feet. Once you're above 8,000.
Once you're above it, then okay, I never thought about that.
It's all constant, and so that's where Michelle's airplane stays. Up there.
Okay. I think I missed some of your numbers, Michelle. So okay, that makes more sense. Yeah.
Yeah, we typically fly in standard commercial airspace between around 24,000 and 32,000 feet to conduct the parabolas. But then takeoff and landing, as I said, is basically the same as a commercial.
Okay. Wow, interesting.
The cabin is usually at 10,000 mean air level.
And I guess, again, this may be a question for all of you, but I believe, Stephen, you mentioned something about doing some tests with blood samples in these parabolic flights. Is there any major change that one just wouldn't guess that happens when you're in a low gravity environment with the human blood?
Marsh?
That was actually my experiment.
Sorry.
I helped.
Stephen saw some of it. So the interesting thing is blood is what we call a non-Newtonian fluid, which means that it does not act like a regular mixture. It's got all the blood cells in it. It's got the white cells in it. It's got chemicals in it. So whereas water or a single type of oil may flow smoothly. You get clumps and bumps, and it's not as smooth, and it wets oddly. And so when Stephen was talking about wetting, what he's talking about, like if you imagine water landing on a freshly waxed car and it beads up and it just slides off, that's an example of the wetting angle. And so, and if you have something like sand and the water just sucks into it. So the answer is for blood, that's not consistent and it acts strangely. And in fact, it's so difficult. It's like what we call computationally expensive to model it. So trying to simulate that on the ground is almost impossible to do. So that's why we actually have to do the experiments with blood in true weightlessness, because it doesn't act like what we predict.
I never knew that it was a non-Newtonian fluid, actually, so it's interesting. And then I can imagine there's a lot of complications then from that.
Yes.
And sorry, Stephen, you had something to say too?
I was just going to say simpler things. I think Mark's covered it great.
Okay. Yeah, very interesting. Very interesting. Okay.
You
so
know,
you
Sean, too, it does point to the fact also, we've kind of circled around it, but zero-G can fly some pretty hazardous materials because of our long relationship and close work with the FAA. Things, you know, Stephen mentioned some of the cryogenics, which are going to be used in the systems now pursuing Moon and Mars. Some deep space missions and some other activities. It is very difficult to fly cryogenics or blood or other hazardous materials. So, you know, these gentlemen are doing some amazing things, as are all of our researchers. And behind that is a very robust and security and safety driven program that analyzes all of those cases and ensures that when we fly them, that they're either connected to our overboard vent system, which we would utilize for any toxic gases, or some experiments are using high heat based on our electrical panels and some other elements available on the aircraft. So just wanted to point that out.
Yes, wonderful. Thank you very much. That's all fascinating information. I'm keeping an eye on the chat boxes and Q&A, and it looks like you've gotten to most of the questions, all of them, I believe. Yes, so any additional insights or suggestions for us as we pursue the parabolic flights you offer?
I would add for the audience, if you got kids, nieces, nephews interested in aerospace, come check out Purdue.
Definitely good advice. Thank you.
Thank you so much, everybody. We really appreciate your time today, and let us know if you have any more questions. We're here to support.
Okay, well, thank you, everyone. I believe that ends our session. And I want to say triple or quadruple thank you to Marsh, Michelle, and Stephen for joining us. Very fascinating discussions, and we look forward to seeing you again.
Thank you.
Thank you
Thank
for the
you.
invitation.
Thank you, everybody. Goodbye.
Thank you, everyone.
Bye-bye.